The nebular theory is our idea of how the solar system formed. The solar system formed out of a huge cloud of gas and dust. And that cloud of gas and dust is a nebula, and it would have been located inside of our own Milky Way. And at some point, it would have started collapsing in on itself, getting denser and denser. Now, when we look at nebulas, they don't just spontaneously collapse in on themselves. They don't really have enough gravity to start the collapse. So we think that a nebula needs to be triggered first. So a shock wave from an exploding supernova somewhere nearby will shock the nebula, squeeze it a little bit, and that'll make it a little bit more dense, which makes gravity stronger. And then once gravity gets a little bit stronger, then it just keeps going. Once it's made unstable, it just keeps going. So once you have this nebula that's collapsing, it's going to do several things. It's going to collapse down into a spinning disk. And if you want a number, maybe that spinning disk is going to be maybe 200 AU across. As it collapses, it's going to do three things. It's going to heat, it's going to spin faster, and it's going to flatten out. The heating comes from conservation of energy. When the nebula was larger, those gas particles and dust particles had the ability to fall inwards. So beforehand they would have had gravitational potential energy. But once they start falling in, they're going to change from gravitational potential energy to kinetic energy. And kinetic energy of a gas you can call thermal energy. So as it collapses, it heats up. Presuming that your nebula would have had a tiny bit of rotation, as it collapses, that amount of rotation is going to speed up. All right? Remember conservation of angular momentum. As something shrinks, it speeds up. So now you've got all these gas particles and dust particles spinning around quickly, and some of them are going to be in stable orbits. All the things that are along the plane are going to be a stable orbit. But some things that might orbit above the plane, up in here, they might have a stable orbit. They're going around the center, but they're going to bump in to all the material that's already in the plane. And eventually, through collision after collision after collision, bumping into things in the plane, it will either get accreted into the protostar or just start orbiting in the plane. So just through collisions between all of the dust particles, collisions between all of the gas molecules, they will agree on one average plane that they should all orbit on. So at the end, you've got a heated, spinning, flat disk. And let's look at what is in that disk. We're going to break it down into four main categories. The first category is metals. Second category is rock, carbon, silicon, etc. Third category is hydrogen compounds. That would include water, methane, and ammonia. And the fourth category is hydrogen and helium gas. Hydrogen and helium gas is by far the most abundant ingredient in the nebula. There's much less of the hydrogen compounds, even less rock, and tiny, tiny amounts of metal. So, you've got these four types of ingredients. The last thing in this table is condensation temperature. Right? Condensation temperature basically means the boundary between when it's a vapor, so a gas, and when it is a crystal or a droplet. And these condensation temperatures matter because only droplets and crystals can be accreted by gravity into a planet. So now let's introduce the frost line and talk about these condensation temperatures a little bit more. The frost line is going to be a temperature boundary. When you're too close to the forming sun, water, ammonia and methane, the hydrogen compounds, cannot form droplets or crystals, so they cannot help you form planets. What can exist in here to help you form planets is the rock and the metal. Okay. When you're further away from the sun, the water, the methane, and the ammonia can all of a sudden condense. And that's going to allow gravity to bundle it up and help you build your planets. So the inner planets are only able to gather up metal and rock. Right? So the inner planets are rocky. The outer planets first started forming with only metal, rock, and ices. Okay? They haven't yet had a chance to become gas giants yet. We're going to come to that later. The terrestrial planets are the smallest, right? That's because there's hardly any metal and hardly any rock to work with. The Jovian planets are bigger because they had more ingredients available. So, you've got these little flakes of material out in your solar nebula. They have condensed, and now we have to start bundling them up. At first, they're going to bundle up with just static electricity. They're going to bump into each other, and there might be a weak electrical attraction, and so they'll bundle up. One particle will bump into another one, and they'll form a set of two. Two will bump into another set of two and form four. Four bumps into a four and makes eight, right? It grows exponentially. But at some point, they get big enough that their gravity is going to matter. And their gravity is then going to draw them into each other. And we call that step accretion. And so you're going to start off with lots and lots and lots of smaller objects that have been built through static electricity. But they'll bump into each other and gravity will help, and they will accrete into even bigger pieces. As they get more massive, they're going to get more gravity. They're going to draw each other together more strongly, and the impacts are going to be more energetic. All right, this would be the era of heavy bombardment right in here. And gravity is going to keep trying to draw things together, bigger pieces and bigger pieces, until your solar system is pretty clean and organized, and you can't accrete anything more. That period of heavy bombardment that we just mentioned, first of all, it's got an awesome name. Right? That's when the planets are forming, and they're forming through asteroid impact after asteroid impact after asteroid impact after comet impact. And that period should last about 100 million years. Earth is forming inside the frost line, so it's really only forming with rock and metal, which when you look at the bulk of the Earth, it's mostly rock and metal. But Earth does have quite a bit of water on the surface, and we shouldn't have really formed with the extra water. So we think it came from some stray comets out past the frost line, got thrown at us, probably by Jupiter, and comet impacts would bring water to Earth. Some of the objects, instead of actually hitting a planet, would slingshot around it. And so we think that there's a lot of stuff that's been thrown out into the Oort cloud. Unfortunately, the Oort cloud is amazingly far away. The stuff out there would be cold, cold asteroids, cold, cold comets. It's really too small and too faint for us to see. We do occasionally see a comet fall back from the Oort cloud, but we don't have any great pictures to show you. The Jovians then did one extra thing so that they could become gas giants. Right? Once they build up a core of rock and metal and ices, and that core is going to be about 10 times Earth's mass, it's going to get enough gravity that it can suck in the hydrogen and helium gas and hold it. So I'm going to press play over here, and here's the core, 10 times Earth's mass of mostly ice, and it's going to just pull in more material, which makes it more massive, which lets it pull in more gas, which makes it more massive, etc., etc. Eventually it's going to run out of gas. Here's an animation of the forming solar system. Protosun would be right here. We've got a tiny seed in here, but you can't see it yet. And the seed here is going to be moving through this disk of gas. And the colors are going to show the density of the gas. So there's the planet seed down in there, your Jovian. And it's making ripples in the gas. And the gas is getting extra dense there, that's the yellow. And right about now, that planet has cleared out its region of gas. It has sucked up all the gas and dust in here that it could. It is still being able to pull a little bit of gas from the inner solar system through this streamer. And it's able to pull in some gas through this streamer. And this gas might still have some rock and metal pieces in it. And if you look in here, can you see the swirl around the planet? The Jovians made their own little mini disks around themselves. Right? They're collapsing gas around themselves now. It's going to flatten into a little disk. And instead of forming planets around a star, we're going to do it in miniature. We're going to form moons around the planet. And those moons are going to be icy because most of the material out here that's condensed is ice. Jupiter is a good example of this. It has 4 moons around it that are really quite large. They all have organized orbits, like they formed from a disk. They'll rotate in the same way, orbit the same way. And all 4 of its moons are quite icy. So let's look at the Jovians. All 4 of them should have been able to gather up rock, metal, and ice and get that initial core. And then that initial core would be able to suck in the hydrogen and helium gas and grow much bigger. So why is Jupiter the biggest? We think that the solar nebula at Jupiter's location was more dense. So it would have been able to get to that core built faster, and it would have had first dibs on all of the nebular gases around. By the time Saturn's core was ready, Jupiter had already started taking the gas. And Uranus and Neptune, they got the leavings. There's one more part to this story. At some point, the star starts to fuse and turns on. And when the star starts to emit a lot of extra light and solar wind, it's going to blow the gases away. And so Uranus and Neptune's core had only just started sucking in hydrogen and helium gas when the solar system's disk was being cleared away by the energy from the forming sun.